tree representation using array. Let us see how we can represent a tree using array data structure. So we already know tree structure looks something like this. There will be a parent. The parent will have children. Each of those children, they'll have further children. This is how a tree looks like. How can we represent this using arrays? So in array, we know there is indexing. So let us say these are the elements in the array. So they will be indexed as 0, 1, 2, 3 and so on. So if you want to represent this tree in the array, the basic requirement is that you should be in some way able to map these indices to the elements of the tree. Then only you can represent this tree using array. So it is not easy to represent any random tree space efficiently in an array. So what we generally do is we in the most common array representation that is used, we generally do it only for complete binary trees. It can be done for all binary trees, but generally we use it more often if it is a complete binary tree. So complete binary tree, we already learned in the last lecture. What is it? All the levels till the last level, till the last but one level should be completely filled, and in the last level whatever is filled should be filled from left to right. This is the rule for complete binary tree. That is, whatever you see here, this is a complete binary tree. So this is a perfect binary tree. So even if you remove this, it will still hold complete binary tree rules, because all these levels are completely filled and the last level is filled from left to right. What if I remove this node as well? Still it is a complete binary tree, because all these are completely filled. In the last level it is filled from left to right. What if I remove this node, this child? Now it is not a complete binary tree, because the last level is not filled from left to right. Because if it is filled from left to right, there should have been this child. So this is how a complete binary tree is. So if it is a complete binary tree, you can represent it using an array very efficiently. Even if it is not a complete binary tree, let us say it is just a binary tree, still you can represent it using the arrays. But the problem is there will be wastage of space, because you will have to leave those indices which are corresponding to those nodes which are not present. Let us say these are not present. Let us say this is your tree. So here this right child is not present here, but you will have to leave the space in the array for this right child. That is the problem if you are representing a binary tree which is not a complete binary tree using arrays. So let us consider this is a complete binary tree. How do you put it in the array? You will do in level order. That is, let us put some data and then understand. That will be easier. Let us say this node is 10. Its children are, let's say, 20 and 30. And the children of 20 are, let's say, 11 and 12. And the children of 30 are 21 and 22. Let us say this is the tree. How do you represent it? You do it in level order traversal. So 10 is stored in index 0, 20 is stored in index 1, that is 20 is the second node. What is the third node? 30. 30 is stored in index 2. Then you store 11, 12, 21 and 22. So you are doing this in level order. So whenever you are using array in order to store a data structure, the basic expectation is that you should be directly able to index any position, because that is the advantage of arrays. What is the greatest advantage of arrays? You can directly go to, let us say, index 3 and access the element. So whenever you are using arrays, the expectation is that if I want to access any particular element in the tree, I should be directly able to access it using array data structure. So how do I do this here? That is the biggest question. So for any node, let us say node is I. If I want to identify the left child of that node, I should go to 2i plus 1. If I go to the index 2i plus 1, I am supposed to get the left child. What if I want to see the right child? If I want to see the right child, I should go to the index 2i plus 2. So this is the basic rule in when you are representing tree using arrays. And what if I want to go to the parent? If I want to go to the parent, I should go to I minus 1 divided by 2. So this is integer division, that is you should take floor. Let us see this practically, whether it is following or not. Let us say I am taking this node with value 30. So the node with value 30 is stored in index 2. So if I do 2i plus 1, what will I get? 2 is the index, so 2 into 2 is 4, 4 plus 1 is 5. So if I do 2i plus 1, I get 5. What is there in index 5? Value 21. What, according to a rule, 2i plus 1 should be the index of the left child. So what is the left child of 30? It is 21. So it is correct. What is the right child of 30? Right child of 30, let us see, 30 is in index 2. So 2i plus, for right child it should be 2i plus 2. So it will give you 2 into 2, 4 plus 2 is 6. What is stored in index 6? It is 22, and it is the right child of 30. It is correct. So whenever you want to get the left child of any node, you can simply do 2i plus 2. And if whenever you want to get the right child, you can do, for left child you can do 2i plus 1, and for right child you can do 2i plus 2. What if I want to get the parent? Let us say I want to get the parent of 12. 12 is stored in index 4. So if I do I minus 1 by 2 with index 4, I am going to do I minus 1 divided by 2, and I'll take floor. So what is I minus 1? 4 is I, so I minus 1 is 3. 3 by 2 is 1.5. What is the floor of 1.5? 1. So what is it? Index 1. Index 1, you have 20. So we were searching for parent of 12 and you got 20, which is correct. So with array representation, whenever you want to find the parent, you will do floor of I minus 1 by 2. Whenever you want to get the left child, you will get 2i plus 1. And whenever you want to do right child, whenever you want to find right child, you will do 2i plus 2. So this is the representation used using arrays. What if some of these are not there? That is, what if it is not a complete binary tree? Let us say it is something like this. It doesn't have these two children. Okay. In this case, 10, 20, 30, these are present, but 11 and 12 are not present. Here the problem is you cannot store any values in 3 and 4. You cannot shift this 21 and 22 here, because if you do that, it will violate the rule which says left child is 2i plus 1, right child is 2i plus 2. This rule will be violated if you shift these elements here. So you have to imagine it is a complete binary tree and leave those positions. If it is actually not a complete binary tree, if it is simply binary tree which is having some missing nodes, then you should leave those positions in the array representation. So if it is a very sparse tree, then it can so happen that you may waste a lot of space if you are using array representation. That is this particular array representation. This is the most commonly used array representation. So the only problem is this: if it is not a complete binary tree, it may lead to wastage of space. So we'll see one more array representation that is used. So this is not so commonly used, but I'm just explaining this so that you stay aware that this also exists. So this is a child array representation. So how you do this is, we use a data structure like a list, where each node stores a list of its children. So I'll just show this with an example that will be easier. So let us say this is my tree. I have, let us say A is the root. Then let us say, so this is applicable for any kind of tree, be it tertiary, n-ary, generic tree, whatever. So let us say B, C, D are the children, and let us say B doesn't have any children. Let us say C has E and F as children. So if this is my tree, so if it is a binary, a complete binary tree, you will anyway use the representation that we previously saw. So if it is not a complete binary tree or not even a binary tree, any n-ary tree, then you can go for this representation of arrays using arrays. So how you do is, you prepare a list. In this list, you will store each of the nodes in order. So for each of the node, you will store list of its children. So first node is A. What about A? A has children B, C and D. So in place of A, that is in level order, you will place the names of children in a list. So the children are B, C, and D. So that is the first node. In place of A, you placed B, C, D, the children of A. Next comes B. So in place of B, B doesn't have any children. So you keep an empty list. Next is C. C has two children, E and F. E and F. Next is D. D doesn't have any children. So you place an empty list. Next is E. E also doesn't have any children. E doesn't have any children. Same case with F. So this is the list that you have. Let us try reconstructing this tree from the list. Then you can say that it is correctly represented using this list. So at the node you have A, and from A you have three children, B, C, and D. B, C, D. Next is B. B is not having any children. So good. Next E and F. So C is having two children, E and F. Then you have D, no children, E, no children, F, no children. So this is the other array representation. This is not commonly used, but the advantage is this particular representation can be used for any generic tree, not just binary tree.